Hi, and welcome to our first reading of our book, Quantum Atom Optics, Theory and Applications to Quantum Technology. So, as we announced last week, what we're going to now do is to go through some sections of our book and explain in a kind of informal manner what the material of these sections are talking about. So what we're going to start with is chapter 1 today. And in chapter 1, what we talk about is basically the mathematical notation of how you write down quantum many-body systems. So here's the chapter overview. So what we're going to start with today specifically is talking about second quantization. So this is how we write down like a system involving many quantum particles. And later on, what we're going to talk about are things like Fock states, multi-mode Fock states, which in a cold atomic system, you will have many different types of particles, say in many different spin states, and so we will need this language of multi-mode Fock states. And then later on, we'll talk about how to include interactions into this whole picture. So, so let's get started with chapter 1 here. So, in section 1.1 is just a sort of an introduction. This is more or less what I just said. And in section 1.2, we're going to talk about second quantization. So in second quantization, what I kind of assume that you already know are that you've probably done like a quantum mechanics course already, and so I'm assuming that you're sort of familiar with things like the Schrödinger equation and basically how that all works on a single particle level. So equations 1.1 and 1.2 are really just sort of talking about so if we have a Schrödinger equation, we can have eigenstates which are labeled by this state psi of k. And these are the usual variables that probably you're already familiar with. And really the question here is, okay, so that's perfectly fine on a single particle level, but if we had more than one particle, then what do we do? So, of course, the way that we kind of learn in elementary quantum mechanics is that, you just have a multi-particle wave function. So we have our wave function, and for each particle that we have, then we have, a particular variable. For example, if it's position, then we have a position variable for each one. So that's great, but what if these particles are also, the underlying particles were, say, bosonic, and they are all indistinguishable particles? So I'm sure you probably also learned that, which is that essentially we need to then symmetrize the wave function, or if they're fermions, then you need to anti-symmetrize the wave function. This is sort of a postulate of quantum mechanics, if you like. And so that's, of course, a totally valid way to do it. But actually in practice, when you work with these things, it's just far more efficient if you work with the notation of second quantized operators. And so originally second quantized operators, of course, come up in the context of harmonic oscillators, right? But actually in the context that we're dealing with here, instead of thinking of these as ladder operators going up and down the harmonic oscillator spectrum, it's kind of the way that we sort of picture it in this context is that essentially we are either creating or destroying a single particle. So, for example, in the case that we're going to be dealing with here, often these operators like A, which obey these bosonic commutation relations, are actually creation and destruction operators for individual atoms. And so when we have these commutation relations here, what this is referring to is that we have, say, a particle at position x, so this might be an atom, and that atom is being destroyed or created according to these operators. These have the usual kind of commutation relations. So an A dagger is equal to, in this case, a delta function, because we're dealing with the continuous spectrum. If we were to deal with the discrete spectrum, this would be like a Kronecker delta. And of course, so for two annihilation operators or two creation operators, this would be equal to 0 because these operators commute. So for fermions, very similar type of relations hold, except that these are now anti-commutation relations. And so anti-commutation, of course, that means that instead of it being A times A dagger minus A dagger A, this will be a plus sign between them. So C dagger plus C dagger C is equal to this delta function. And then the similar type of anti-commutation relations actually hold in this way. So you should note that these cases also have a plus sign. So this means things like if you ever have two fermions at different positions, when you interchange them, then you'll get a minus sign between them. So I think this type of thing is commonly taught in quantum mechanics courses, and but what's kind of quite a useful sort of trick that you can actually use in this context is that, well, what we kind of defined here is with respect to a particular position. So we can sort of visualize this in terms of, say, this figure. So for example, say these are different positions that an atom can occupy. So essentially what creation or annihilation at X means is really, what that really means is that at a particular kind of position here, you're either creating or destroying a particle, and the colors here are supposed to signify that these are basically different quantum states that the bosons can occupy. So position is really just one particular type of orthogonal wave functions, because of course if you take the overlap of these types of wave functions, if they're at different positions, they would be of course orthogonal. But we don't have to just have wave functions at particular positions. So we could easily also have different types of orthogonal states. And so we can equally actually define bosonic operators with respect to other types of eigenstates, which I'm going to label here by K. So this is why we started off this discussion by saying that here are some of these orthogonal states. So these would be the orthogonal states that would be arising from diagonalizing some particular Hamiltonian. So, for example, here, I've got something that looks a bit like a harmonic oscillator. And so, as you'd be familiar with, then the eigenstates of such an operator are in at least one dimensions. They look like this. So the lowest energy state is a Gaussian, and then you have these higher order wave functions where there's an extra node for each state that you go up. So we can actually define these bosonic operators also in terms of this basis too. And then, so the way that we do that is that we essentially do something like we essentially multiply this AX operator, which means that we're annihilating a boson at position X, and then we integrate that with respect to whatever orthogonal functions that we're talking about. So we can just picture these states as being, for example, these states. So this will be like K equals 0, K equals 1, K equals 2, K equals 3. And so for each type of integration, essentially what we're doing is kind of a change of basis of what we are using as our underlying sort of variable. So instead of working in the basis of x here, which was a position, we're now going to work in this other basis, which is in terms of these labels k, right? And of course, either way, we can describe any kind of wave function that we like on the single particle level. So if you perform a linear combination of these states or these states, we can basically write down any wave function that we like. So in this sense, this is essentially a kind of a basis transformation where we're transforming this bosonic operator from the basis of x into the basis of k. And of course, creation operators are defined in exactly the same way, except that this is the Hermitian conjugate here. Why we can still interpret these things as creation and annihilation operators is that if you take the commutation relation of these bosonic operators in a different basis, so for example this one and this one, then they still satisfy the same type of commutation relations that we're used to, and because this time it's discrete, this is a Kronecker delta. And over here we again have this same type of zero commutation relation if we're dealing with two annihilation operators or two creation operators. Okay, so that's basically the content of this section 1.2. So let's also go through a couple of these exercises here. So in exercise 1.2.1, it says to verify equation 1.9. So let me just do that now. Okay, so 1.9, so we need to verify 1.9. So we start with this relation. So we need to substitute in these quantities. So let's go ahead and do that. So A of k is defined like here. So this is going to be commutation relation of dx psi k star x and a position x, comma, with this guy here, which is another integral here. And so what we need to make sure here is that the integration variable is, we don't use the same integration variable, otherwise we'll get confused with the one over here. So let's just make that change of variable, and whoops, I've already stop there. Okay, so it's psi of L here, and this is a dagger of x dash. Okay, and then let's take the integrals out of this commutator, because this is actually, if you have a sum of commutators, it's the same as the commutators of the sum. So we're allowed to take out the integrals here, and because these are just scalar factors, we can also just take them outside of the commutator. So this will be L x dash, and then so what we just got left here is a x and a dagger x dash. Then we can go back and use the result that we had earlier on, which is that a and a dagger with different positions just equate to a delta function. So this part of it we can replace with that delta function. So then this integral here collapses to basically the same variable. Okay, and then we'll have psi k star x and then psi L of x. And this is basically just the orthogonality relation. So if k is equal to L, then this will be basically the same thing squared, and by normalization that will be equal to 1. So this will be equal to 1 if k is equal to L, and if k is not equal to L, then these will be orthogonal functions, so these will be equal to 0, so k not equal to L, and you just get that. Okay, and for the fermion version, so, 1.10, I think this one is a little bit more straightforward, because basically you just do the same thing, you substitute in these definitions, and then because the original values of the a's at 0, so this will automatically equal 0. 1.2.2 is talking about the fermion version. So in this case, we again try and satisfy these analogous relations. And basically the argument for that is extremely similar. Essentially substitute the definitions, and then instead of an anti-commutator here, you'll get, instead of a commutator here, we'll get an anti-commutator here, and then the remaining argument is the same. Okay, so hopefully that was a bit helpful to understand this section. So if you like these videos, then please subscribe to our channel, and we will continue doing more sections. So thanks for that. Bye.